All right, welcome back to Lean Together 2025. Our first speaker of the morning is Alex Kontorovich, and he's going to be talking to us about complex analysis and PNT plus. Thanks, take it away.
All right, so thanks very much to the organizers for the invitation. It's a great pleasure and honor to speak here. Yeah, let me dive right in and tell you about some of this work. So the PNT project was co-organized with Terry Tao. We were kind of working backwards. FLT is going to need Shepard to do Shepard, a warm up for that is Dirichlet's theorem, and we didn't even have at that time the prime number theorem, never mind in MATLib, like formalized in Lean. So let's dive right in. Now PNT, I think this is one of the most formalized theorems, serious theorems in mathematics. It was done over a decade, 2 decades ago by Jeremy in Isabel. Then you see the list of people. So a lot of people had done either a combinatorial proof, the Erdős-Selberg proof, or a Fourier analytic proof, Newman's method. And we wanted to do something that would extend to much more general settings. You could probably, I haven't thought about this yet. I'm sure you can do Shepard
Yeah, I unfortunately I have a 3 o'clock.
Oh,
But no, which is a real shame. But my main, unfortunately I do have to run.
okay, there we go. Sorry, somebody was didn't mean to. Where was I? I thought someone was reacting to my claim that this was one of the more proved theorems, and well, maybe there's more things that have been done. Anyway, yeah. So this is an experiment, and this is also an experiment in building a rocket. Like in math, we are really responsible for every single theorem down to the axioms ourselves. But can we build something with where you buy parts off the shelf because they've been written in such a way that you know exactly how it can or can't be used. So that's not something new. This is we're following. Terry had just completed this polynomial Freiman-Rouge formalization and lots of other similar projects, the sphere aversion project, the liquid tensor experiment. So as usual, we're going to be using GitHub with Blueprint and Zulip. And one little innovation that Ian Yausling and I came up with was usually in Blueprint, you have a separate tech file where you write all the tech, and then you have a separate Lean file where you do the formalization. Now, if halfway through, you wrote all the tech and you start doing the formalization, you realize you want to do a couple of extra things. Well, now you have to like go back to the tech file and make sure that these things are properly connected. And what we did is we added a little scraper so that when you add this delimiter, so this delimiter, this slash minus, Lean knows ignore everything that goes afterwards, but then we put the two ampersands, and now the scraper will take this tech and turn that into a separate tech file, and then that'll go into Blueprint. And so this allows you to have the natural language right next to the formal language as you're writing, which is also really, really useful for people that have Copilot turned on, because you get to in real time constantly see the state of the art in auto formalization. So this was the natural language text. I put the cursor here. For all I know, Lean, it's Microsoft's Copilot. Microsoft Copilot has read these things or is following some pattern that what it's suggesting is exactly the formal version of the theorem that's written here in tech, but for obvious reasons, this drastically speeds up your workflow. So that's another bit of help. And Paul Nelson even has a version of this in Emacs. I would love a VS extension where the tech, instead of looking like tech, I still have to parse these dollar signs and backslashes, but the tech for him is locally formatted. So he just sees like nice mathematical text next to nice formal text. So that would be really cool if somebody wanted to do that. Okay. By the way, please interrupt at any time with any questions, comments. If you want to put anything in the chat, like let's have a conversation. So far, so good? Okay. So So how's it going? So we opened the project to the public on January 31st, and you're more than welcome to. I'll show you afterwards how to set it up if you want. The proof of the prime number theorem itself was completed on April 8th, so a little over a month later. This was not at all a race. We did a lot more than what was needed just for a direct attack on PNT. The original project, in fact, comprised 3 different attacks. One is using just Fourier methods. So this is the Wiener-Ikehara Tauberian theorem. I realize not everyone here is a number theorist or knows complex analysis. So it doesn't matter what these words are if they don't make any sense to you. They're not. I'm not going to use them at all. I should say Michael Stahl had already done a ton of work that reduced the prime number theorem just to this Tauberian theorem. And now this Tauberian theorem is done. That's what was finished on April 8th. We also wanted to do we wanted to do some complex analysis and see how to do complex. A lot of my talk is going to be about complex analysis. So how do you pull infinite vertical contours past poles, pick up residues, this kind of thing. We were going to develop Mellon transform API. A lot of that was already done by David Loeffler, so we're building on top of his work. And then goal 3 was to finish with a classical savings in the prime number theorem of order e to the minus root log x. And that was going to use either Hadamard's factorization or local versions. I'll talk about that more in a second. In the meanwhile, so these 2 authors, Song and Yao, in Isabelle, went straight to part 3. Apparently, I couldn't track down when they actually announced that they had done it. My guess is something like mid-March. And in their paper, they say the formalization took 1 month. So maybe they were inspired by PNT Plus, or maybe it was just in the air that someone should do this. Of course, they're working on top of the much larger complex analysis library in Isabelle. There's a model that we could try to copy to get to part 3. But I'll explain in a second why I want to do it in a slightly different way. Okay. Any questions on that so far? So far, so good. Okay, let me keep going. There's not so much time. So this was also a great excuse to get a bunch of other things into MATLib. We didn't have Fourier inversion. Now we do, thanks to Sebastian Gazelle. We didn't have even the Fourier transform of the Schwartz function is Schwartz. So with Sebastian and Heather Macbeth and Loeffler and Vincent Pafara, eventually we got this. So this kind of like, standard analysis, this was an excuse. It was going to be in MATLib. Eventually, this was an excuse to get it into MATLib. And so we're still missing a large database for one of the mid to late undergrad or early grad areas in MATLib, and which is needed for a lot of analytic number theory, namely complex analysis. So let's zoom in on complex analysis for a minute. So yeah, so I first heard about lean from a talk of Kevin's in September 2019. I had to chase this down to figure out when actually this was going on. And at the time I was teaching complex analysis, so I thought I could help. Eventually I did a project with an undergraduate at Rutgers, Brandon Gomes, where we formalized the statement of the Riemann hypothesis, but that didn't use complex analysis, and we never put that in MATLib, so it's just floating out there in Neverland. But so you go back to, what did I do on lecture 1 of complex analysis? Well, you want to integrate holomorphic functions along curves. So what is that? Well, a curve is an equivalence class of parametrizations, and this is what you want to do. You need a derivative over here. What kind of curves? Well, you don't want just like differentiable curves. You want to be able to do some angles. So you want like piecewise continuously differentiable curves. And for MATLib, we'll want even more general, like maybe just curves whose derivatives are integrable, not necessarily continuous. Okay, so what's the exact structure that we're looking for? Like maybe a curve is a map from R to C, and then a set of points where you have these jump discontinuities, or is it a sequence? Is it a finite sequence? Is it an arbitrary accountable sequence? And then do you want to be differentiable on open intervals, or is it closed intervals? Is it like when you start thinking about what you actually want, you fall into this paralysis of choices that you'll need to make before you can even get started that will drastically impact what you do thereafter and whether you're able to make progress or not. So it's, as a human being, of course, it's super easy to just say this and move on without a moment's thought. But these decisions are really, really important. I learned one cool idea from Vincent Bafara, which is that you can avoid the word piecewise altogether. And this is a little trick that if you have a curve that you want to have a corner, then when you can like compose with smooth functions that come to a stop at the corner, and then start also with speed 0, and then the derivative is continuous. So then forget about piecewise, but you now aren't just integrating at unit speed around whatever you're doing. Fine. So another very well-known problem, if you want to be doing Cauchy integrals and picking up residues, you need to know when you have a closed curve that inside the closed curve your function is holomorphic. And what does inside mean? So that's the Jordan curve theorem. It's been formalized before. Hales did it. It's done in Mizar, again, 20 years ago. It's notoriously tedious, tens of thousands of lines of code. And anyway, the final version of it that will go into MATLAB will be a statement about reduced integral homology groups of Rn minus the k-sphere. And so what do? Twiddle your thumbs and wait until someone does that, right? And just don't get started. So I don't want to twiddle my thumbs. I want to get started. So I learned from Eli Stein. I took complex. I was very lucky to take complex analysis from Eli, and his whole approach is never mind about general curves. We know what to do for very particular kinds of curves, and these keyhole contours are all you will ever need. So you just draw. If you have a ball minus a point where you know that a function is holomorphic, then you integrate over a region that looks like this, and take limits, and everything works out. You want to code this up? You want to explain to Lean what exactly this curve is? And by the way, then precompose and postcompose with functions that slow down so you can take a speed 0 at the corners. Like, this is going to be absolutely a god-awful mess, and no one's going to ever do it. So at some point I had sort of the big realization. I mean, it's a triviality, but that you can do all of the complex analysis you need for analytic number theory just using rectangles. And we had a test case of this with Ian Yasling, where we proved that if you have a holomorphic function on the disk, that function has a primitive, has an antiderivative. And we developed this rectangle technology for that. So that was sort of a test. We're still, that PR is still sitting in PR hell, and I have to get back to it at some point. That's on me. But so how does this work? So we have Green's theorem in MATLAB, thanks to Yuri. So we know that the integral of a holomorphic function over a rectangle, as long as, yeah, you guys are all Lean experts, so you can read this. So if we have a set U of the complex numbers and a function that's holomorphic on U, and a rectangle that's contained inside U. Now, what's a rectangle? A rectangle is defined by two corners, Z and W, two complex numbers, Z and W, and I don't know which one is where, but they're two opposite corners. So we'll use this. This is the closed interval where I don't care about the order. So this is what a rectangle is, a complex rectangle. And then if the complex rectangle is contained inside your set U, and your holomorphic function is holomorphic on U, then the rectangle of integral of f from z to w on this rectangle z to w is 0. So we have that. So what? How does that help us? It helps us because rectangles tile rectangles, unlike disks, which do not tile disks finitely. I mean, that's the Apollonian circle packings explain how disks tile disks. So if you imagine you have a holomorphic function on a rectangle minus a point. So you have a pole at this point. Well, what you can do is you chop that big rectangle into 9 smaller rectangles, and on 8 of them, and of course the integrals on top, going in opposite directions cancel out. So the conclusion was a disk, but the technique was rectangles. Sorry, Kevin, I don't understand. Maybe you can ask your question now or later.
You said on the previous slide you were proving Cauchy for a disk.
You mean on this slide?
Maybe.
Yeah, this is like the standard proof.
Okay.
Of Cauchy on a disk, and it involves these keyhole contours. And I'm going to give a non-standard proof.
Go forward one step.
Yeah.
There. Holomorphic functions on disks have primitives.
Oh, this.
Do we know that? There.
Yes, that's the PR that it looks like.
Okay. So the conclusion is a disk. But the
It's
technique is
true that it's a
rectangles.
disk. Yes, it's true that it's a disk, but the way you get the way you
Yeah, I got
you
it.
can go from rectangles to disks. And in fact, we have
Nice.
another in progress work that will extend this from disks to arbitrary regions, arbitrary simply connected domains. Yeah, it's true that the conclusion was a disk, but that's because rectangles fit inside disks nicely. And disks are nice to describe, and then if you have some open set, well, open means you have disks, and so you can patch things together. Yeah, thanks for pointing that out. But that technique was rectangles, yeah. Which is following the Stein-Shikarchi technique of using triangles. So instead of, it turns out that triangles are not as nice to work with as rectangles. I was surprised by that. Okay. Any other questions in the meantime? So we have this, we know that, yeah, that's what I was starting to say. Rectangles tell rectangles. And so what you really want to do, the whole point of that keyhole contour is to zoom in on a little disk around the singularity. And there you can do a small, you can use the fact that the function is, has an expansion to take a residue. So how do you do that here? So you chop the rectangle into 9 smaller rectangles. 8 of them have integral 0. And so you zoom in to a square around a pole where you're facing integrals like this. So ds over s on a rectangle that goes from minus epsilon minus I epsilon to epsilon plus I epsilon once you renormalize things. And so if you parametrize that, you're looking at integrals like dx over x minus I epsilon. And so what? Now you need the theory of complex logs. We actually have a logarithm function for the complex numbers in MATLib. Personally, I don't like it because it's not sort of the canonical one, but it can be made to work. But I wanted a proof that didn't need this complex log. And the very simple but pleasant observation is that when you add the bottom and the top together, you have these two integrals that add together to actually make a real valued integral with 1 over with d arctan. And so we know how to integrate arctan, and so you get pi I over the top and bottom, and you get another pi I over the two sides, and ta-da, you get the residue theorem for simple poles. Okay, so what about pulling contours? So you want to do things like prove Mellon, Mellon's, you need Perron's formula for Mellon transforms and Mellon inverses. And the human proof is you just pull the contour to the left or to the right, depending on if x is bigger than 1 or less than 1. But what is that? That's adding and subtracting rectangles. There's rectangles, and then there's little U-shaped and cap-shaped things that need to be sent to infinity. So a little bit of limits and adding, subtracting rectangles, and you get Perron's formula. By the way, let me point out that for some reason, analytic number theorists use smoothing systematically everywhere, except when they get to the prime number theorem. And then they start putting in explicit functions, and I don't understand why this is happening. I think it's just because it's such an old subject, you can't help but go back to the way people used to do it. But in the PNT Plus project, we systematically use smoothing. So notice the difference between dx over s times s plus 1. That's the version that converges absolutely, and the version that's in the literature and in other formalizations where they have x to the s over s. And now you have to cut the integral. You can't go all the way out to infinity. You have to cut the integral, and then you have these error terms that are floating around everywhere. Like it's you can push it through. It's not that it's technically impossible. It's just very, very annoying. And I wanted something that was going to be actually pleasant to formalize. Okay, so what about, the next step is going to be in the natural language proof, you just quote Hadamard factorization. So you have an entire function of finite order, and you have a countable set of zeros. And so the function can be realized as this Hadamard factorization. How do you even say this formally? I mean, I can think of, again, 10 different ways to say it, but what's a way to say it that's actually going to work? Like, how do you formalize this notion and have it be not a nightmare to deal with? Like, so finding the right structures is difficult. So we don't need necessarily the entire version of this. All we need is really a local version. There's a theorem of Borel-Carathéodory, which again, now you want to say, I want the zeros of f in this ball. and I want to sum, logarithmic derivative of this, compare it to f, and I get this bound. These are very easy things to explain when you draw pictures. And the hard part is when you're doing formalization, you can't tell Lean, here's a picture that explains why something's true. Okay, so let me try to finish up. So the point is, there's actual math that still needs to be worked out. Like, what are these objects really? What's the right definition for them? When we do it in informal language, we say all kinds of things that feel like they're formal. We have theorems and axioms and so on, but they're really not. So then one of the next goals is to build up this complex analysis that we discussed. We already have elementary arguments like partial summation, and that should prove the prime number theorem with an error savings like e to the root, not e to the root log x, but e to the 1/10 root log x. So the classical error term replaces this 1/10 by a half. The best known today in informal language is 3/5 by different methods, and it's an exercise to improve 3/5 to 1. That's the Riemann hypothesis. Anyway, so this error term would already be better than any power of log, so more than enough for any application. In the meantime, Michael Stahl has pushed things from just the prime number theorem to Dirichlet's theorem. So on the horizon, we want to head to Shebetarov. We need to get this stuff into MATLib. It's getting, it's getting too far away from MATLib. We need to sort of pause work that way and get work going back this way. We need a lot more automation. I learned this philosophy from Heather Macbeth. You should, if you want to prove a plus b equals b plus a, you should not know the word adcom. Rewrite adcom is the wrong way to prove a plus b equals b plus a. The proof is by ring. So you should know big tactics that handle entire swaths of mathematics, like what is the reason that this is happening, like a meta reason, and there should be a tactic that handles that meta reason. You should never know actual theorem names. And if you do that, you just might get the De Bruijn factor below 1. And the second you get the De Bruijn, there's this instant that the De Bruijn factor goes below 1 that everyone will want to work formally. Every mathematician, if you're not working formally, you're actually working harder than you should be. So this is, my analogy is when Knuth got the Knuth factor below 1. It is now easier to just tech your paper yourself than handwrite it, hand it to a secretary, and ask the secretary to typeset, which is how things worked 40 years ago. You get the Knuth factor below 1, everybody switches to tech. Sorry to the secretaries that used to typeset these things for us. You get the De Bruijn factor below 1, everyone will be doing formalization. And I buy Heather's argument that the way to De Bruijn factor below 1 is to not ever know the names of theorems. Have tactics that handle entire swaths of mathematics for you. You just know what, this is true because we're working in a ring. So the answer is by ring. Okay, so let me stop there. Thank you very much.